Hello, my name is Jason Richards, and I'm a student at the University of Rochester. I want to thank my mentors, Dr. Yang and Dr. Talapatra, and of course the project sponsors, Texas A&M University and Los Alamos Laboratory. The title of this project is Catalytic Dimethyl Ether, or DME, Steam Reforming by Density Functional Theory, DFT. So an outline for this project is the background and introduction, and then the quantum mechanics explaining the DFT calculations, and then the next steps and research goals. So the mission of Los Alamos National Laboratory is to solve national security challenges through simultaneous excellence, which is exactly what they've been doing for the past 3 months with me as we've been working on this project. So new developments in catalyst structure have shown to improve hydrogen selectivity and yield from DME steam reforming, making it to where it would be possible maybe one day for a hydrogen economy by producing lots of hydrogen from this DME steam reforming. So why use DME? So dimethyl ether is a renewable fuel and a great hydrogen carrier, making it really great for this project and for use in the future. So using density functional theory through the VOS software, you can simulate chemical reactions that are possible to understand the hydrogen yield and reaction mechanisms without having to do them in person with real-life experiments. So we've been comparing these simulated chemical reactions with the in-person experiments to see how they compare. So the research focus is catalyst testing through VOS and DFT. So to investigate the hydrogen yield and reaction mechanisms of DME and catalysts, they are calculated through this VOS software through the GRACE portal, which is through the TMEU, through the university, which uses DFT and quantum mechanics. This research attempts to find the most optimal molecular structure for a catalyst to have the best hydrogen selectivity with DME and use the least amount of energy possible, which is important. And then several different catalysts were used, including cobalt, beryllium, nickel, and their physical mixtures. So you can see here of a submitted job through the VOS software and the GRACE portal. So you can see I have multiple jobs running, and yes, example of a submitted calculation. So what makes this possible? So quantum mechanics makes this possible to do this in a simulated setting. So any material on Earth consists of nothing else than a bunch of atoms, ions, and electrons bound together by electric forces. And all of these forms of matter can be explained by one simple equation, the many-particle Schrödinger equation, which really is not that simple because it's very difficult to solve and takes a long time to calculate. Hence, VOS uses the Born-Oppenheimer approximation, which neglects the motion of the nuclei to simulate chemical reactions, making it to where it can calculate much faster and makes it possible. So the DFT calculations or reactions. So to put it more simply, DFT VOS finds the lowest energy or most optimal structures, which allows one to predict which catalysts perform better than others. Find the best one to produce the most hydrogen, of course. So every calculation requires input files, including the in-car, K-points, post-car, and the pot-car. So a real important one is the in-car, as you can see on the left, for beryllium nickel and beryllium O2 reaction. And you can see here all the parameters for a simulated molecular structure. And then on the right, you can see an example of a postcard for beryllium nickel and CeO2 reaction, which shows some of the parameters for Ce4 and Ce nickel. So a lot of these input files can actually be found online through the Materials Project website, and they can give you a lot of information and a lot of input files for these calculations, which is very helpful. So some of the DFT calculations that were running a structural optimization calculation of CeO2. As you can see, CeO2, a visual of it on the bottom left, and reaction with DME, this is also in figure 3 on the bottom, resulted in finding an optimized lattice parameter of 5.4653a. So an optimized lattice parameter, so a lattice parameter, as you can see on the right, has an A, B, and C, so a three-dimensional axis with with angles between, three-dimensional angles. So that's what creates the most optimal distance between each molecule or each electron. So, and then after that, I carried through a DFT plus U calculation for the same structure using a value of U equals 4.5 eV applied to the CE 4F states. And then the optimized lattice parameter was equal to 5.4979A, which is very similar to the first one, only off by 0.03, which is not much at all, which is consistent with the previously reported experimental and theoretical values. So the software is proving to be very similar to the real-life experimental values, which is great news. So another calculation I was ran with the nickel Cu. So replacing one lattice ceruleum on the topmost layer of a CeO2 system. These slabs were modeled with 9 atomic layers containing a 2x2 unit cell, and then during optimization, the top 6 atomic layers were fully relaxed until the force was no less than 0.05 eV per A, whereas other atoms were fixed, making it isolated. To avoid the artificial interactions along the z direction between its periodic images, a vacuum space with a length of 12A was employed, which is just, like I said before, the lattice parameter, a distance of 12. So for next steps and research goals, continuing calculations with different catalyst combinations should produce a lot more opportunities to find optimized chemical reactions, improve hydrogen selectivity, and improve hydrogen yield, which in the future could create a lot of hydrogen with less energy in case non-renewable fuels do eventually run out someday maybe, and this could be a great alternative. Also discovering molecular structures that provide the least energy necessary to provide the more hydrogen for a potentially hydrogen-based economy. So this is truly an experiment that could be utilized one day in the future for a hydrogen-based economy, and in a larger scale could really be utilized by lots of people as a renewable fuel. Thank you. I want to thank everyone for allowing me to be part of this experiment.